one really good skill to have in not only math, but in everywhere, is when is a decimal a good answer and when is an exact answer a good answer. So a lot of times in math, we don't want a decimal. Like a decimal is approximating. So it's like when you type in the square root of 50 on your calculator, unless you have one of them fancy calculators that gives you the simplified square root, it gives you an approximation. It just goes on forever. These are irrational numbers if they're not perfect squares. So we want to talk about simplifying them, which means breaking them up and taking out all the perfect squares and leaving the other numbers underneath the radical. So square root of 50, you can think of a lot of things multiplied with the square root of 50, right? You could be like 10 times 5 gives me 50. But that's no good because neither 10 nor 5 are perfect square numbers. So what I say when I teach my kids how to do this, and number 2 will spend a lot more time in doing this, is think of 2 numbers that multiply to give you 50. One of them is a perfect square. So when you think of a perfect square that goes into 50, 25. So you can break this up as the square root of 25 times the square root of 2. Because you're allowed to break up square roots into multiplication. And then what is the square root of 25? Can you take the square root of 2 without it being decimal? Which means the simplified answer for the square root of 50 is 5 square root of 2. And you probably vaguely remember doing this with the quadratic formula last year. Yes? Maybe you blocked it out. So I threw a whole bunch of different ones here. Like number 2 is kind of a little like opposite of number 1. There's also this number here that's outside of the square root. You can't just leave it alone. What's the square root of 8 times the square root of 4 going to be? Oh yeah, I guess I could have done it this way. Did you take the square root of 4? Is that what you did first? What did you do? Nothing? I was going to multiply my square roots together. Because just like I can break it up as a multiplication, I can multiply them together to put it back as one square root. The square root of 4 is already a perfect square, right? So, the square root of 8 is perfect. And can I say 2 square root of 4 is the same as 2 times 2? So is that the same as 4 square root of 8? How do I know if it's completely simplified? When there's no more perfect squares under the square root. So you have to look at 8 and say, are there any perfect squares under 8? Yeah, 8 is divisible by 4, and 4 is a perfect square number. Don't forget this 4's out here, still hanging around. So I can write this as the square root of 4 times the square root of 2. And again, you're probably not going to write this many things down, but I just want to show you my thinking. If the square root of 4 is 2, again, I can't take the square root of 2 out. So the best answer here is that simplifies to 8. Kind of having that list of perfect squares in your head is a really good idea. Like 4, 9, 16, 25, 36, 49, 81, 100, 121, 144, 136, gotta move it. Alright, what about this one? It looks scary because it's a fraction. But, what do you notice about 49? Is 49 a perfect square number? What about 36? What's the square root of 49? What's the square root of 36? Oh my gosh! You think I want you to take 7 divided by 6 on your calculator? No, I want to like this. A nice answer. No decimals. I've been building you up to this, right? Our hatred of it. Oh my goodness. I skipped number 3. 76. That's the answer. Because we took the square root. The square root of 49 is 7. Ah!
Got it.
That was really loud. I bet that's going to be on the recording.
Shut. Ah, did you hear that? Got it.
Okay. What about number 3? Do you remember simplifying with letters under the square root last year? We're not really going to do that much right now, I don't think. But I thought while we were reviewing, we could go ahead and do this. Just like with 8, you take out the part that's a perfect square and you leave the leftover underneath. You can do that with Because do you agree you could, like, the square root of x squared, what's that always be? Because the square root and the square root won't cancel out. Okay, so let's talk about 18 first. Can you think of any perfect square numbers that go into 18? So can I break 18 up as a square root of 9 and a square root of 2? I can. So now you have some options here, and it's whatever makes the most sense to you. A to the 5th. We could break these up by a squares, or we could go bigger than that if you want, but let's just do a squared to first, and I'll see if you see that. A to the 5th. Is that the same as saying the square root of a squared, and the square root of a squared, and then an extra a left over? Is that the same as a to the 5th? It's 2. Why am I going to do this? Because every time you take the square root of something squared, like it cancels each other out. And I can do that for each one of these. Or maybe you can see something else I do here. But b to the 4th, how could I rewrite b to the 4th? B squared and b squared.
Nah.
What about c to the 7th? B squared and c squared and c squared and a c. I know there's really not really a need to do all this. And grow up. Oh.
You went quiet when I said that.
Yeah.
I thought I was being quiet.
So, just like up here, it's just kind of out of control here now. Take out everything that's a perfect square. What's the square root of 9? If I have the square root of a squared and the square root of a squared, do you agree I'm going to get a times a out of that? So I'm going to go ahead and say that's a squared. So that's gone. How many b's can I take out? The square root of b squared is just b. The square root of b squared is just b. So that's b squared. How about c? And this will be c times c times c. How can I make that c to the 3rd? And then anything that's not a perfect square gets stuck back under the square root. Kind of like the old days of the remainder, right? So what's left over? I got a 2 left over, I got an a left over, and I got a c left over. What's a way simpler?
I really wish this was
So, a lot simpler way than writing all this out is if you see a to the 5th, how to do it. You can see, how do you know that there will be 2 out here and 1 left over? If you have an odd exponent, are you always going to have 1 left over on the inside? Always. If you have an even exponent, are you going to ever have any left over? No. And so you can write it all out every time. The shortcut is, it's just half of the exponent. So like if you had the square root of b to the 100th power, the idea is that you wouldn't have to write b squared out that many times, that you would say, oh, well, that should be the 50th, because that would be 50 perfect squares. Again, we're not going to do a whole lot with letters right now in this chapter, but we are going to do a whole lot with square roots, so I just want to throw that in there. And one more thing here, we don't usually like square roots in the bottom of our fraction. We think it doesn't look right. We like to move them from the bottom to the top. And so what could I multiply the square root of 3 by that would make the square root of 3 go away? Right? If I multiplied by just 1/2, the 2's would cancel out, but I'd have that square root of 3. But if I multiplied by the square root of 3 times the square root of 3, isn't that going to always make that a perfect square? And I'm only allowed to do that if I do the same thing to the top. So on the top, I'm going to have 2 times the square root of 3, which I can't do anything with. I'm just going to leave it like that. What am I going to have on the bottom? Yeah, the square root of 9, which is just 3. And there's this whole debate when we get to when you get to pre-calculus. We'll talk about it more. Do we still need to do this? We call this rationalizing the denominator, meaning we want a rational number in the denominator. Some math people say that that's for old school people when they didn't have calculators and that we don't need to do it anymore. But a lot of books still do it, so that's why I'm showing it to you. All right, so in this chapter, if I asked you for an exact answer, or pretty much unless I ask you for a decimal and you get a square root, I want you to get in the habit of simplifying these square roots. All right, and we're going to practice a lot with this. We're going to practice it through the notes and on the homework today, and see that we're just going to simplify these square roots. And the more you do it, the better you're going to do it. Okay, so chapter 8 is called Right Triangles and Trigonometry. This is the whole SOHCAHTOA thing I've been telling you about. We're not there yet, but that's what we're going to learn about in this chapter eventually. I know, Alan's not even here. But there's all these things that are really cool about right triangles and how we can solve things using right triangles. Today we're going to talk about this idea of a geometric mean, which if you want to open your book up, you can, that you can kind of follow along, but it's up to you. I think it's really smart. You know what I like to do? I like to open my book up when my teacher's teaching, and then sometimes I find out the answer by just reading the book, and then I seem smart. So geometric mean, I feel like the words are kind of confusing sometimes, but it says when the means of a proportion are the same number, that number is called the geometric mean of the extreme. Mean of the extreme is too bright. So what that means, and it's kind of written in this next box, which I know the copier didn't do a great job, so feel free to kind of go back over anything you can't see. But it means, means too much. When one diagonal of your proportion is the same, and they talk about it being the means, but it could be the extremes. It just means when one diagonal is the same, it's always going to work out the same way. If we cross multiplied here, do you see that we would get x squared equals a times b? And if you solve that every time, how do you get rid of x squared? You square root it. That when they ask you for the geometric mean, you can set up a proportion, but the idea is the geometric mean is just taking the square root of the other two numbers. Or a lot of times they'll just say, find the geometric mean of these two numbers, and it means just taking the square root of multiplying them together. So this is what you need to know. Geometric mean. So notice on this one, it says the geometric mean of a equals 9 and b equals 4 is 6, because the square root of 9 times 4 is the square root of 36, and the square root of 36 is 6. A lot of times the geometric mean is not going to work out nicely, which means I want you to give me an exact answer. Sometimes it'll say give an exact answer and round to the nearest tenth, and so that way you can check with your calculator as well. Right? So I think that's what that is. Find the geometric mean between 2 and 50. So this is kind of just a formula that you need to know, that the geometric mean is just going to be the square root of 2 times 50. What's 2 times 50? 100. And what's the square root of 100? 10. Well, that one worked out so nicely. And again, it's like saying, just if you want to think the proportion way, it's like saying 2 over x equals x over 50. That's what you're setting up there every time. So you don't ever have to do that if you just remember the formula. So maybe let's do one that doesn't work out nicely. Find the geometric mean between 12 and 15. 12 times 15. So now we have to think of what number is going to 180. You know tricks about how to know if numbers going to numbers? Yes. Yes. But like, there's some shortcut ways. Like, you know how to tell if the number. How do you tell if a number is divisible by 2? How do you know if a number is divisible by 3? You add up all the digits that equals to a number divisible by 3, then it's divisible by 3. The same thing works for 9. If you add up the digits in a number and it adds up to a number divisible by 9, then that means 9 goes into it. It's not really needed for 180, but for really big numbers, it's sometimes really nice to know. For 4, do you know how to tell if a number goes into 4? 4 goes into a number. Definitely has to be even. Like, you could always just check if 2 goes into it twice. I think the little divisibility rule is if 4 goes into the last 2 digits of the number, then it goes into the number. And for 8, if it goes into the last 3 digits of the number, then 8 goes into it. Isn't that kind of weird? I don't know any shortcut for 7. 7's just a weird number, right? Like, try it. The 7's not a perfect square. Yeah, I don't know. A lot bit, right? So anyway, 90 and 2 definitely gives you 180, but 90 or 2 aren't perfect squares. So for me, I always try to pick one number that's a perfect square. So instead of picking 90, I'm going to pick 9, all right? Because I want to make it a perfect square. And 9 times what gives me 180? So now here's the hard part of simplifying radicals, right? 9 is definitely a perfect square. We could say 3 squared root of 20. But you're not done unless this number has no perfect squares in it. Does 20 have any perfect squares left in it? Yeah, so you always have to look and say, can I break that down any more? So for me, I like to keep them all under square roots until the very end. If you want to go ahead and say the square root of 9 is 3, you can. But I'm going to, underneath this, say that's the same as the square root of 4 times the square root of 5. If you wanted to, apparently 9 times 4 is 36. Apparently 36 went into 180, but I didn't know that. So just know that you might have to take a few steps there. So now I would get 3 times 2, which is 6 square root of 5. Eric. Okay, how? Okay, go. That's right.
I was just like, yeah, I thought like, I was certain numbers, I thought like, well then again, if you have a calculator, I mean like,
you could just divide by 7, right? But, it works though. On your homework maybe, on your homework quiz tomorrow, I know, it says give the exact answer and round to 1 decimal. Round to 1 decimal means I want you to plug it in your calculator. Does it matter whether I plug in my calculator the square root of 180 or I plug in 6 square root of 5? Because it's the exact same thing, and you could actually check on your calculator, if you weren't sure if you did this right, that the decimal for 6 square root of 5 better equal the same decimal as the square root of 180. I'm not a big decimal fan, which means I don't know that I'm really going to ask you for the decimal, but it doesn't hurt to know that this is approximately 13.4. That's the approximate answer. That's the exact answer. And you know, with Khan Academy, sometimes on there, right, if you, like, McKinsey just solved problems and stuff like my 6-hour class, they solved an equation that didn't work out nicely, and they put the decimal in, and they marked it wrong, because it wasn't a decimal. So just saying 13.4 was the wrong answer, because they want the exact answer. They would want Okay. The rest of these are all about triangles and basically how we can use geometric means to solve for some stuff. So it says if the altitude is drawn to the hypotenuse of a right triangle, right? If we talk about what the hypotenuse of a right triangle is, it's along the side, right? The one across the right angle. Then the 2 triangles formed are similar to the original triangle and to each other. I was looking at this over the weekend because I felt like, again, I'm not a super visual person, and I would have to break this up every time. Again, there's no way I could look at this one picture and see all that, I feel. But that's just how my brain works. But it says, so if the altitude, remember the altitude is a segment drawn in that forms a right angle with the other side, basically like the height of the triangle. If it's drawn to the hypotenuse, then it makes those two smaller triangles, triangle ACD and triangle CDD, and all three of the triangles, the big one, ACB, ACD, and CDD are all similar, which means all the stuff we did last chapter with setting up proportions would also work to solve for missing sides in there, and it kind of leads us to these next theorems about how we can solve for missing sides if this is thrown in. But on your homework today, you have this exact same type of question. Given this picture, can you write a similarity statement identifying all three triangles, mostly making sure you match up the corresponding angles, right? And if it helps you, you can separate them. If you can do it without looking, you can do it without looking. So what's the big triangle? What do you want to call it? EFG, that sounds like a good choice. And we know that that's going to be similar to the medium-sized triangle and this little triangle. Do we need to separate it? Don't we separate it? It's my favorite trick. I want to teach geometry next week. Right? Probably maybe the easiest thing to match them up is matching up hypotenuse to hypotenuse, right? So on EG is our hypotenuse, right? So on this one, FG is my hypotenuse. Do you agree with that? So I need to make sure that, like this, F and G have to be in the same E and G, which means what goes in the middle have to be F and G. Careful there. Don't want to get camera friendly. Right? So using the right one.
Give one example.
You follow me on this whole idea of the hypotenuse? Like, the right angle has to be the same as, like, the right angle is the biggest side in all of them. The biggest sides are going to be similar to the biggest side. So in my little triangle, what is the hypotenuse? EF. The hypotenuse of the big triangle was EG. So I know that EF has to be similar to EG, sorry. EG has to be similar to EF. So similar to, can I say EF? Can I do this? Or does that matter? Should it be FEG? FGE? Match them up, right? Why am I doing this? Why are you letting me use the same letters? What should this be? Not G in here. Did I use the right letter in this? Oh, children. This should be H. Sorry. I've gone crazy. You guys tell me that. Like, there's no E in this one. Right? It's FHG. I just was using the same letters over here.
That's what I was doing.
And on this one, I was just filling in what was missing, but it wasn't the right thing. We want to make sure the sides match up, so let's check really quick. Like looking at this picture, FH is the shortest, right? FH is the shortest, and what's the shortest side over here is FE. So that matches FH with FE. Like those are matching up. So the shortest sides have to go together, the longest side has to go together. And on that one, my shortest side would be what? EH? On this one? what's my right angle in the biggest triangle? No, the great big one here. My right angle is F, right? What's my right angle in this triangle? So those have to be in the same spot, right? And in that one, it's also H. So all those right angles, those letters have to be in the same spot, however you choose to write it. Well, I mean, I said F, H, and EF, but remember we talked about when we did similarity things that, like, you can say EF and FH as long as the angles are corresponding. Does that make sense? Like, I might have said it backwards. Maybe I should have said EF and not FE, but I was just going with the segments that are proportional. To me, maybe some people just see this and they're very visual people. I'm not, which is why I take forever to look at it. Like, I literally draw it out and I match up angle with angle, side with side, short side with short side, long side with long side. Some people just see it right away, and if you're one of those people, then just write it out. But I just want to make sure you understand that there is a method there of making sure that the order does matter. Okay? Okay. Last things here, and I was doing this last hour. I was working out some problems on here to make sure that that I could use these, and we'll talk about this later on. Maybe this test you get to have like an index card that you can write some formulas down, or maybe this will just be really easy to do because it's just using geometric mean. But to me, I kept looking at the formula to do it the first time. But it says if the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments, then the length of this altitude is the geometric mean between the lengths of these two segments. So notice, same picture as before, right? Here's my altitude, but now it's saying that this is the geometric mean between these two segments. So you can say that if you wanted to find the height of the triangle and you know what x and y are, you can always just set up a proportion because they're similar triangles. We could say x over h is equal to h over y, and again, it's just matching up proportional parts. Or if you remember that that's just the geometric mean, right, because the h's are the same, that means every time if you wanted to find the altitude of a right triangle and you know these lengths here, you can just take the square root of x times y, because that's the geometric mean. So whichever way makes the most sense to you. That's going to probably be the least amount of work, but you could always just set up proportional parts if you want. And then we can use the same idea to solve for the other side of the triangle as well. And again, once we learn trig, I think that using this formula is silly because once you learn trig, you can solve for sides of a right triangle a lot easier than doing this. But the same idea, because we have these similar triangles, and I'm not going to read all this, but it basically just says we have all these similar triangles. Notice C is the entire length of AB, right? It's the entire length of the hypotenuse. X and Y are still the same. Now we have these segments up here called A and B. Not a coincidence that that's how they're labeled. The angle C is across from side C. Angle B is across from side B. Angle A is across from side A. That's where that's coming from. But again, we can just set up some proportions here. So we can say, notice C is the big side. C over B will always be equal to B over X. And again, it's just the big side of the big triangle over the hypotenuse of the littlest triangle. And again, that's just geometric mean there. And you can also set up the same thing to solve for A, that C over A is going to be equal to A over Y. And again, if you drew out those three separate triangles like we just did, it's just matching up proportional parts like we did last chapter. It just seems a little crazier with all those letters here. And if you just memorize the A equals Y over C, I would like to do that. But okay, right. Yes. Yep. It's the same idea, use them. Okay, so it says find C, D, and E. Here's the thing, you can't find some of them until you find something else. So the question is, looking at this, looking at those formulas that you just had in front of you, probably looking at the paper that was on mine, which one of those letters do you think we can solve for first? C, D.
What?
Yeah, you've got to solve for the altitude first, I think. Well, maybe not, but I think we do. And so E kind of becomes H in this picture, right? And it's just telling us that the altitude is always going to be the geometric mean between those two numbers, cutting up the hypotenuse. So we can say E is going to equal the square root of 6 times 24. Which, oh my goodness, works out so nicely to be 144. And what is the square root of 144? Maybe we don't do that. Maybe I was just being silly about that. I always thought these first. Okay, so to find C and D, you have to use the geometric mean leg theorem. And either you memorize this formula, or you can... You can't solve Pythagorean theorem if you only know one side, right?
What are you talking about? Now we got E, we can solve for E using 6.
Yeah. Alright. I'm doing this way though, but you can do Pythagorean theorem. Even with Pythagorean theorem, I want exact answers, right? Not decimals. So, but yes, you're right. You could do Pythagorean theorem. If I was going to set it up like this, then I would say you have to use this entire length, right? So that's an entire length of 30. Well, I could say, I don't know why I'm writing this. I'm going to say D equals the square root of the long side, which is 30, times the short side, which is 6. Let's see if we get the same answer. We should get the same answer, or we've done something wrong. We didn't have this earlier. 180. Did you get 180? 144 plus 36. But yeah, definitely Pythagorean theorem works. I didn't even see that, so that probably is less confusing than this, right? No, we want exact. So yeah, I think that was the same as 36 times 5, right? Remember earlier we did 9 times 20, and then we broke 20 down again. So I want 6 square root of 5. And then definitely now, even if you didn't notice Pythagorean theorem on D, you definitely could do Pythagorean theorem for C. And so totally that option if you want to do Pythagorean theorem. Just make sure you remember the hypotenuse is the biggest side, so don't miss it because you set the wrong one. The next lesson in this chapter is called Pythagorean theorem. But I'm gonna go ahead and set it up using these proportions just so you can see it. And I'm gonna say that A equals the square root again of the longest side. Now it's times the bigger side of this. But that's really not as confusing as I thought it was the first time I did it. Sorry, not. I was looking at it. Right, so it's the missing leg is equal to the longest side, the hypotenuse, times the shorter segment. But that's the shorter leg. The longer leg is equal to the square root of the hypotenuse times the longer segment of the hypotenuse. We're just matching those up, so that makes sense. Right? The bigger the number, like the harder it is sometimes to come up with numbers in it. So sometimes I like to pick bigger numbers, like S ten. Right. Definitely. Yes, I saw this like the 72 right away with the 9. I was just wondering if there was something else that goes into it bigger than 9. And totally, just like the one we did before, we could start with 9 and then break it down. Like 9 and 80 goes into 9 times 80 is 720, and then we could break 80 down more. The 90 isn't a perfect square, right? We could, but then we have to keep breaking it down. You see what I'm saying? So I don't know. We want to just stick with 9? Do you want to do, okay, so what did I say, 9 times 80? Then what can I take at 80? 16. I went one bigger than 4, right? Because 4 goes into 80, so I went ahead and checked. Does 16 go into 80? Because 16 is a perfect square, and it does. The calculator helped me here. So I'm going to go ahead and say, instead of doing 4 and 20 and then having to break 20 down again, I'm going to break that up as 16 times 5. So then that's going to be 3 times 4 times the square root of 5, or 12 square root of 5. And if you want to get the decimal there, you can as well. I want us to practice with our square roots. Just like that. But yeah, I thought that was going to be a lot worse than it was. It's really not that bad, especially because you can use Pythagorean theorem, and you get the same. Definitely a way to check your work. So, I think this is the last, is this the last one? So don't yell the answer out, but just check for a minute and see if you can, it's just E, F's missing there too, but just E, notice that E is the, well that's just silly. You could just do Pythagorean theorem, right? I don't think even teach us this silly trick. Right. I should appreciate Pythagorean theorem. Yeah. You get, I mean, it's the same answer every time. It's why Pythagorean theorem works so well. I did it the new way, where I took the geometric mean of 16 plus 4, which is 20, times the bigger segment of the hypotenuse. But you get the same thing if you take 16 squared plus 8 squared to equal E, which is your hypotenuse. E squared, take the square root of it. Notice they have decimals over there. Oh, decimals, which is the easy way out, right? Square root of 320 as a decimal is... So, is the exact answer you need? Is that what you said? So I could break this up as 16 times 20. I could break 20 up as 4 times 5, right? So I'd get 4 times 2, 8 square root of 5. So I will tell you that your book is kind of bad with the decimals, and we are going straight for a book, and we're going to do better than this. Right side of life, go ahead. Okay, 2 of them say find x, y, z.